Seismic failure modes get a little more complicated because the system response becomes a function of both earthquake and stage. But calculations will generally follow the same process. Here's how it would look in an event tree format where we have the branches for the different PGA intervals, and then for each of those ground motions, we will have a full set of intervals for the flood duration, which leads into the failure branches. The annual probability of failure is still equal to the hazard probability times the system response, and the average annual life loss is still equal to the annual probability of failure times the exposure-weighted consequences. Note that for pool, we are using the stage duration curve, not the stage frequency curve. We do this because we want to know what fraction of time in a year the reservoir exceeds a specific stage. We can then multiply that by the annual probability of a specific earthquake to get the combined and coincident probability. Instead of being able to do the calculations one column at a time, each column becomes a table for a seismic failure mode. Two-way interpolation for the system response probabilities will be required. Past that, all the calculations are the same, there's just a lot more of them. This brings us to example 3.3, where we will calculate the risk for a seismic embankment failure mode. Pay close attention to this example because you will be doing very similar calculations for homework 3 at the end of the module. In this example, we are given a simple event tree, the seismic hazard relationship, and the stage duration relationship. Our first task is to calculate the joint loading probabilities. We will start by interpolating off the stage duration relationship to get the duration exceedance probability for each headwater of the ranges at the top of the table. The headwater ranges were given to us in this example, but to get even intervals, we would follow the same discretization procedure that we've been using for the stage frequency of hydraulic hazard failure modes. We will always use linear interpolation when interpolating from a stage duration relationship. Once we have those probabilities, we subtract the duration exceedance probability, or DEP, for headwater B from the DEP for headwater A. We were told to include non-exceedance in the first interval, but because the DEP for headwater A is 1, we do not need to add anything. The non-exceedance probability would be 1 minus 1, which is equal to 0. We can drag the relationships to the right to complete the first few rows. The only formula that will be different is the last one, where we have the exceedance probability. The probability will be equal to the DEP of elevation 2108.5, which is 1.29 times 10 to the minus 6. Next, we will follow the same procedure for the seismic hazard, but we will use semi-log interpolation. Using ln log int, we interpolate the annual exceedance probability of PGA A. And again for the PGA B AEP. We can drag that formula down to complete all but the last row of the table. The last row is for the exceedance probability, which will be the AEP for a PGA of 1G. Like for the headwater at the top of the table, the PGA intervals were given to us. If we'd been required to generate these intervals on our own, we would have used the same discretization procedure described in Module 2, just like we did for the headwater a few slides ago. Subtract the AEP for PGA B from the AEP of PGA A, but include the non-exceedance probability in the first cell, which is equal to 1 minus the AEP of PGA A. And again, the last probability in the column will be for the exceedance probability. To get the joint or coincident probability, we will multiply the headwater probability by the PGA probability to complete the table. Be sure to lock the headwater row and the PGA column in the formula so that you can drag it over and down. When done correctly, the sum of all the joint probabilities will sum to 1, as shown here. With the joint loading probabilities complete, let's move to the PFM risk calculation, starting with the system response table. We are told to use linear interpolation because of all the zeros in the system response, so we will use the by_lin int function. The first input into the formula is the midpoint headwater. The second is the midpoint PGA, followed by the headwater range from the system response table, then the PGA range from the same table, then the system response probabilities, followed by 2 ones since both the PGA and stage are in ascending order, followed by 2 zeros because we are not extrapolating. In the formula, lock the row for the initial headwater input and lock the column for the initial PGA input. Lock both rows and columns for all other cell references in the formula so that we can drag and drop. Here is the completed system response table. Next, we will calculate the annual probability of failure. APF is equal to the joint loading probability multiplied by the system response for each interval. Then drag and drop to finish out the table. Next, we need our exposure weighted life loss. Life loss is a function of stage, not PGA. As such, life loss will only change with a change in stage. It will not change with a change in PGA. To get the incremental life loss, we interpolate using the midpoint stage. The incremental life loss is equal to the day exposure times the quantity of the day breach life loss minus the day non-breach life loss, plus the night exposure times the quantity of the night breach life loss minus the night non-breach life loss. Be sure to lock the rows and columns for the exposure values in the formula and lock the row for the stage inputs. Drag and drop to complete the table. The average annual life loss will then be equal to the annual probability of failure multiplied by the exposure weighted life loss. Now we are ready to sum things up again to get the total risk for the failure mode. Sum all the annual probability of failure values from the annual probability of failure table to get the total annual probability of failure. Sum all the average annual life loss values from the average annual life loss table to get the total average annual life loss. Then divide the average annual life loss by the annual probability of failure to get n bar. The resulting FN plot will look like this, with the total plotting just above the low probability high consequence box. For seismic failure modes, the RMC joint loading probability toolbox can be used to develop the joint loading matrix and to help screen them for inclusion as potential risk drivers. This toolbox can be downloaded from the RMC website under Software, RMC Toolboxes, and then Risk Calculation Suite. In the toolbox, on the earthquake hazard worksheet, the site coordinates and the source are input. Then the seismic hazard data is input. In the flood hazard worksheet, the stage duration relationship is input. First, the elevation datum is selected, followed by the method for extrapolating the stage duration relationship and the required inputs. When period of record or detail level are selected, the stage duration used will be as input by the user. If screening level is selected, the user will be prompted for a set of inputs, and the spreadsheet will extrapolate the stage duration relationship to the upper bound peak reservoir stage defined. For this method, only the period of record is input in the yellow cells at the bottom of the sheet. The spreadsheet will automatically add the upper bound stage input from the prior step. Next, the exposure and life loss consequence estimates can be input, which will be used in a later step to calculate the average annual incremental life loss. In the risk screening worksheet, the user will define the headwater and peak ground acceleration partitions to evaluate. Earthquake and flood thresholds can be input at the top of the sheet. If these thresholds are left blank, the spreadsheet will return a true joint loading probability matrix. When defined, the spreadsheet assumes failure will not occur for earthquakes in stages less than the defined thresholds. The spreadsheet will also calculate an annual probability of failure, assuming certain failure, a system response equal to 1, above these thresholds. This is useful information when screening potential failure modes. When the calculated annual probability of failure is very low, the failure mode can likely be excluded without additional analysis. Also in the risk screening worksheet, the average annual incremental life loss is calculated using the life loss consequences and the earthquake and flood threshold inputs.